The talk today is lessons learned from generalizing natural language processing beyond English. Basically, not English, question mark. So I'm sure most of you have heard the term a polyglot, which is a term for someone who speaks multiple languages. Does anyone know what the term is for someone who speaks only English? Yeah, exactly. American. So the whole goal of this talk is to make our models not be Americans. So some of the things is, this is not a scientific assessment of this, but in NLP 2021, there was 848 papers. 101 had the term multilingual in the title. 97 of those spelled it this way, 4 spelled it some other way. Another 61 had cross-lingual in the title. So yeah, if you look at this, there's a small percentage of our papers that are kind of multilingual or cross-lingual. Like I said, this isn't really scientific at any means. There could be monolingual, Spanish, Chinese, other papers out there, or just have something in the title that's not. But a very small percentage of our models are actually in English, or outside of English. And that's kind of a problem. So the whole focus of the talk today is to talk about why we should be doing things besides English. So this is just kind of, I grabbed an image from the World Atlas of Language Structures, but this one's just noun and genitive word order. And if you look at this spread geographically around the world, you can see that languages exhibit a lot of different morphology, linguistic features, things like that. So the first thing is, if we're only going to focus on English, we're going to miss a lot of aspects of language out there. So I just wanted to talk about some of the popular models out there also, and just kind of point how much of a problem this can be. So Google Translate supports 108 languages. Facebook, aka Meta, has been making a big push recently for no language left behind. So it started with their Flores 101 data set, and now they're up to 200 languages that they're supporting, which, as most of you have probably heard here, there's between 5,000 and 7,000 languages on Earth, depending on how you count. So these are all just a small percentage. If you look at MBERT, this supports 104 languages, and this is one of the most popular models out there that's really transformed everything in the last 3 or 4 years, as you saw from Mark's talk last week. And XLMR has about 100 languages. And this is just some of the more traditional, I guess, foundational models out there, right? But if you look at others like MBART, initially that one had 25 languages, it now supports 50. There's like M2M 100, but again, we're talking about hundreds or low hundreds of languages support for most of the models out there. And I am being a bit harsh right now, and I kind of mentioned this in the abstract of the talk, but one of the reasons is, beforehand, our models, I would say 10 years ago, were not good enough to really necessitate things beyond English, right? Like we weren't doing great on English. So this is just papers with code. I grabbed one of the random tasks, WikiQA. And you can see that like in July of 2014, so only 8 years ago, this map score is below 0.6. And now if you look at something that's over 2 years old, 2.5 years, close to 3 years old now, we're above 0.9. So one of the reasons why we haven't had a lot of these models outside of English is we weren't able to solve English very well in a lot of tasks. And the other thing is data is expensive. So FrameNet, a very popular semantic labeling task, has at this point now, I guess, 9 languages, including English. But the majority of the data is in English. So it's really, really, really expensive to create these sort of data sets. So that's another reason why people haven't been doing it. However, we now kind of have new models out here of deep learning, which has really changed the paradigm, not only in performance, as you're seeing going from 0.6 to 0.9 on like papers with code, but also with the ability that they are able to generalize to other languages without too much work. So yeah, kind of the structure of this talk I'll go through is just different ways that we can actually make our models multilingual, different sort of methods of doing that, and some of the things that we actually learn from this. So I'll start off with talking about zero-shot and few-shot learning. So I'm sure most of you have seen this, but I'll be a little explicit on this. So this is going to be a named entity recognition task. So let's have this training data, which is in English, right? And we have these class labels, which are in orange. And so Johns Hopkins University is in Baltimore, Maryland. The Blue Jays have won 44 national lacrosse championships. And let's say this is what's been annotated by humans. And we train a model that is able to actually predict. Named entity is pretty good nowadays. However, at test time, we might have this, which is Swedish, and it's många studenter bor I Hamden, right? And the goal here is, can we use this English resources to actually evaluate on Swedish? And if our model's pretty good, it might actually pick out that Hamden is a named entity here. So The key to this really is these large multilingual models. I'm sure everyone here has seen MBERT, but because it is so important, I'm just going to walk through very briefly on this again. So this is a mass language model. You can see Johns Hopkins University was founded in 1876. And here we've masked out two words, Hopkins and founded. You put this through a deep neural net, right? And this objective here is to try and predict Hopkins and founded. And this is really useful because it learns the actual structure and pattern and statistics of language. Whereas our previous language models would be something like an n-gram language model where we're generating in a sequence with a fixed length. Here, we're able to learn a lot more about what's actually going on in language. And these models caught on very, very quickly and have been very, very, very useful for improving things in the field. So BERT came out and was in English initially, and pretty quickly you had MBERT, which with my crappy PowerPoint skills here, you can see here has a French beret and a sombrero and some other things. But basically, all this is our monolingual models, right? You're putting in a single language and trying to reconstruct the output after masking. There's a few other tasks they do, but that's about all. So in the zero-shot setting, I'm going to dig into a specific task, cross-language information retrieval. So here you have some sort of input query. Think of this as like a search engine. Often that's what an information retrieval system is, what we think of. So you have some sort of search query in a language, but unfortunately all of your documents are in another language. So here we have Wile Tupui, which is Quechua, and let's say that all our documents are in English, right? So how do we go about doing this? I'll take a step back on this and talk about one of the most transformative models in information retrieval recently. This is a 2020 paper called Colbert. And in this one, what they do, there's a lot of stuff here, but what they have is they're encoding a query, so whatever your search term is basically, and you're encoding documents. And what they do is they use a language model. So they use a BERT-based monolingual model here, right? And there's some sort of ability to calculate a similarity score, this maxim. This was important to the paper, less important for my talk here necessarily. But what's nice here is you could take a pre-trained language model, basically have a score of whether or not documents are relevant or not at training time. So you showed a bunch of a query, bunch of positive examples, bunch of negative examples, and have it start learning things. And you have two copies of your language model here, one for the queries and one for the documents. What's nice about this model then is it learns, like, it fine-tunes BERT, right, for encoding documents. So there's some sort of document representation, and it fine-tunes a query version also. So you have a query sort of model. And then you can pre-compute all the vectors for your documents on a corpus, which is quite useful because if you're trying to search a large corpus, you don't want to be computing BERT scores over the entire corpus at search time. All you have to do then is do the queries and calculate this really quick maxim operation. So this worked really, really well in information retrieval, and 2020 paper, and it's just citations are going crazy right now. So how do we do this in a cross-lingual setting? So in this setting here, we have the same sort of thing, but we're going to introduce a new model called Colbert X. And here, all we've basically done is swap the BERT model with XLMR, which is one of these large language models that I'm sure most of you have heard of, right? So what's happening when we're training our model now, right, is at training time, we put, at training time, we're just doing everything in English. So you have this query, calories in Taco Bell chili cheese burrito, right? And then you have a bunch of documents, some that are relevant, like there are 370 calories in the burrito, and some that are non-relevant, which could just be like fat content or something from another sort of document. And all we do is we tune this model, same we were doing before with the MBERT one, just using XLMR, right? And at test time, we take our English query, throw it through some MT system, and then put it into Colbert X. It's never seen Chinese before, right? This is the zero-shot setting. All it's seen is English data. At test time, we have a bunch of Chinese documents that we're testing on, and we have a query that we've used machine translation to put into Chinese. And like I said, here's this Colbert thing again, and we just swapped out with XLMR instead of MBERT. So for the experiments I'm going to show here, we're going to use the Clear Common Crawl collection, which is easier to say as HC4. And as I was saying, the documents are in Chinese, and we translate the query from English into Chinese. And so this is kind of what it would look like now if we were going to use the same query in the same documents, though, or in documents in Chinese. You'd have this query in English, bunch of Chinese documents, and you're going to translate them. So how does this actually do? This is actually really amazing. So the bar on the left, these are all mean average precision, so higher is better. If you look at the bar on the left, this is if you use a machine translation query from English into Chinese, and then you just have Chinese documents, now a Chinese query, and you run BM25, which is one of the popular statistical models going back years, right? And this one here gets a score just below 0.25. What's amazing is that second bar from the left. So here, if you use a human query, so literally this is the best possible translation you can have of the query. It's not going to have any sort of noise from machine translation. And you're using a model that's been great for years, right? BM25 is the statistical method that's a baseline for so many different papers. And you get a score that's quite a bit of improvement, but it's 0.3. Now, in this zero shot setting here, right, where you just use this MT thing, so basically the first bar and the third bar are comparable, right? But this one, we've not actually shown the model any Chinese. So the BM25 model doesn't have to be tuned or anything for it. For this one here, we're showing it all training examples in English, and you can see a huge performance gain in Chinese. And again, kind of like an upper bound for this would be if we actually use the human translation of this, right? And it gets slightly better. But this is kind of what's amazing about these models is we can train this on our corpora that we've had for years in English, and without doing anything, get really good results on a foreign language. So this is really amazing. Is kind of some of the insights that these models have. But yeah, so that's a zero shot. So that's one way that we were able to actually generalize beyond English, right? So this one here is kind of the simplest. We have a bunch of English data. We use English data to train our models. And then at test time or inference time, we just do it in another language without anything. Now, of course, what would make a little bit more sense is few shot. And in few shot, maybe you don't have the resources to annotate thousands and thousands of documents or more, but maybe you can annotate 10 in a language, especially if you're going to do something like 48 languages or something. So in this work, I wanted to mention briefly gradient surgery. So this is one of these NeurIPS papers that is very machine learning heavy. Came out in 2020, and basically this is for multitask learning. So during this thing, what we'll have is you have two different tasks, and the gradient for your update for one is like the red, and it's pointing one direction, and the gradient for your other task is pointing the opposite. So basically these gradients are saying, hey, step to the left, and then one's saying step to the right a lot, so you're not really getting much information. So this is one of these machine learning papers out there. So they do this method, which is a little bit beyond the scope of this talk here, but what they project to make the gradients orthogonal. This just makes it so that you don't have gradients trying to take a step to the right, a step to the left. It's just, you're losing information that way. And you can do it two ways. So B, basically you project the blue vector over so that they're orthogonal. C, you project the red one over so they're orthogonal. And D just means they're non-conflicting, right? So if they're already, the cosine similarity, I believe, is less than, yeah, if the angle there is less than 90 degrees in this 2D space, you just don't do anything. And this one here, the gradients basically are telling you to go in a specific direction. So one of the important things about why I think we should be talking about languages other than English is this is a very popular method within the machine learning community right now, but we as like natural language processing people deal with a lot of language. So let's say you have a test set with 48 languages. This computation here, as I glossed over it, is actually n squared. So it's a pairwise comparison across all the gradients for all your languages. So if you wanted to actually scale up to 48 languages, this method gets too slow. So this is one of the reasons of why it's really useful, even in a few shot setting, for us to look at this. So yeah, how do we scale to 48 languages? So basically here, I'm going to go over this a bit quickly as well, but if you don't do gradient surgery, this is just basically you train the model with 48 different languages. This is the top. You can see there's not a lot of similarity between gradients across languages. Is this actually necessarily that useful or not? Downstream results show that it's actually better to have gradients. There's probably multiple local optima out there, so it's useful to have gradients going in the same direction. That's kind of the intuition I have for why this is working. But when we do this gradient surgery with stochastic gradient surgery, this is basically we're stochastically doing gradient surgery. And this is a model that was introduced in this paper here with Hao Shu, who's one of the PhD students here. But this actually is a way to do things linearly as opposed to quadratically, because you're stochastically doing it and you're still getting the benefits of it. So this sort of problem doesn't exist in most of the machine learning multitask problems because they're not doing 48 different tasks at once. But when we start scaling to more languages, we see this. And these similar gradients with the darker image here, you can see, actually mean that they're all kind of going towards the same local optima. And there's actually some interesting groupings in the upper left. You can see a lot of Latin-based characters, script languages, In the bottom right, you get different language families and different scripts. So there's actually some information that's being learned in there. And there's a lot of potential future work on this. But kind of the key takeaway from that is that multiple languages actually matter. And why this is also really useful to think about more languages is this. So this is the trite IQA data sets, typologically diverse question answering. If you haven't heard of this data set, it's a really nice data set that came out of Google with Jonathan Clark. Did you have a question?
Yeah, what exactly is gradient similarity? So are you like evaluating this on all?
A cosine similarity. So yeah, for this one here, we're doing a pairwise comparison with all the languages at a specific after the model.
On each language specifically on the examples from that language.
Yeah, exactly. So. Yeah, so in this trite IQA, this is F1 score again. This is better. This is a question answering task, but it's a really well curated data set. If you do zero shot, basically we train our whole model on English using XLMR with some sort of question answering model on top. You're getting a score of almost 56, right? So if we do this few shot learning, like 10 examples, so now we add 10 examples to our training for just 10 examples from each language, you can see the performance actually drops, right? So whereas before we were talking about zero shot works pretty well, it's working well here, you would expect more data would work better, but it doesn't. So when we start thinking about things besides English, it doesn't always assume that if you just add more data, things are going to go up. And this is because it's in such a low resource setting. You only have 10 examples, right? So in this one here, once you do the gradient surgery, and basically, as I was saying, I think the intuition here is there's multiple local optima. When you force them to go towards the same direction, you start getting gains. So you're making gains with the different languages here. So yeah, so that's basically how most people think about these things initially is, hey, I have data out here, I have models, and I can either do something that's zero shot or few shot. But as you start to do this, you start to notice things about the models. Take a step up. And yeah, so that's kind of what most people think of how do we generalize to other languages. And that works pretty well. However, there's other ways to do this. And one nice thing to do is actually create silver data. So we use the term silver data versus gold data. Gold data is like you have human annotators who have actually labeled the correct things. Silver data is, well, we're going to try and make it like treat some data that it's like gold data, but we've created it synthetically. And for here, I'll first jump into data projection. So one of the most common ways to do this is, let's say you have, again, a named entity task here. And it's like Fort McHenry is the site of an important battle in the War of 1812. It took place in Baltimore, Maryland, between the United States and England, right? So let's say we want to get this into Spanish, right? So we just put it through a machine translation system. Hopefully for a lot of languages, we have good enough machine translation systems nowadays that we can actually do this. And then we use some sort of word alignment model. And from that, we can hopefully try and project the annotations. Now, you might miss some, it might miss Baltimore, Maryland, it might miss something because translation's wrong. So these are a noisy process, but it works pretty well. And who knows, like at a certain point, you might have a tag that goes somewhere wrong. I'll jump into this one pretty quickly because Masa did give a seminar last spring on this, I think, with a little bit of this information. But basically what she did is her and a bunch of other collaborators did a very extensive study using named entities, some other tasks, but a lot of semantics and information extraction tasks where they just looked at how does data work. And there's not really a silver bullet for our silver data that's going to solve everything, right? But there's different sort of ways you can do this. So you can take up in the, so you guys, like cursor show up on this? Yeah. So up in here, you can see like, you'll have these source language, which is like English gold annotations. And for this task, we were doing a lot of Arabic stuff. And you're trying to do things such as create machine translation data, right? And then use the word alignment, what I was talking about before. And then you can project these annotations, add this data. So now you add the gold and the silver data together. And then you'll have a model that works a little bit better in these foreign languages. So often using the silver data has huge gains over a zero shot or a few shot setting. Another kind of thing here is you take this gold and silver data, you put it into an encoder and kind of treat it like a zero shot sort of setting. But overall, silver data is just like you're trying to use automatic tools to create new data out there. And they have huge impacts. Like I said, this was something that has been talked about quite a bit in some of the seminars and other people here have worked on it. So I'm going to go pretty quickly through this. And now, well, I'm going to go back to this Colbert X, and I only showed you half of the stuff before. So as we were saying, this worked really well in the zero shot. However, there was another setting that we investigated, which was a translate and train. So in this one, what we did is we actually took all the Chinese data. So we took these English queries and translated them into Chinese, and then actually trained the model naively in Chinese as well. So this one here, you're still doing the same exact thing, but our training data, sorry, that's covering that. Yeah, you still have this training data, and you're just translating all the data from English in your corpus into Chinese and the queries in the Chinese also. So now we've taken, rather than just train this on English and do this in a zero-shot setting, we've done some synthetic thing where we've now translated all of it into Chinese and are doing it in a synthetic setting as well. And then at test time, similar sort of situation as before, where you translate an English query. So the goal with this one is, hey, it's actually seen some Chinese data before, as opposed to just being put into English. Let's see if this goes. And how does this work? Basically, here I'm just going to show you the Colbert X zero shot versus translating train. So the zero shot is what I was mentioning before, translated only on English. These are the red bars. The yellow bars are if you actually translate the training data and then do the same exact thing where you're training an information retrieval model on this. The one on the left, the HC4 Chinese, is the one I showed you before. There's a couple of there's one other HC4 data set, and the other is this clay data sets, the CLEF, they pronounce it clay, on a bunch of languages, similar sort of cross-language information retrieval. And so on 2 of these language pairs, it actually does better in the zero-shot setting, but in a lot of settings, it does help to actually train on the data. So it's just another way that you can actually input silver data into your models and get some useful information out of it. So before I move on to the next part, I was going to see if there's any questions here. All right, not hearing any, that's good. Or terrible, one of the two. So, but yeah, so another way we can kind of use methods besides this in NLP is fine tuning. And this is something you hear a lot about also, is we're going to fine tune X model for this, or we're going to fine tune it for another language. And we were doing this a little bit earlier on with some of these with fine tuning in a different language, like the translate trains. So here I wanted to talk about a gradual fine tuning. So this was some work, again, that came up when you start looking in low resource settings across multiple languages. And this is a paper from 2020. It was presented at a workshop at the ACL. So basically here what you have is your standard sort of model here that you're training, right? This could be any sort of cross-lingual XLMR model for different sort of tasks. And let's say we have a bunch of this orange data on the top, which is out of domain data, but this is where we have a lot of labels. And we have a little bit of in domain data, this blue box here. And so normally what people would do is train both of these together, right? Throw all the data together, and then maybe just fine tune on the blue data, the in domain data. And so that's just like a one-step fine tuning approach, right? So in gradual fine tuning, we kind of looked at this and said, hey, maybe this isn't the correct way for the model to actually go forward. Maybe it needs to kind of be nudged slowly, almost like a curriculum learning approach towards the in-domain data rather than this huge shift. Because especially in these low resource settings, you see a lot of catastrophic forgetting. And yeah, so a lot of times people will talk about, oh, I tried to fine tune my model, but I had catastrophic forgetting. So this was a proposed method that helps in a lot of situations for that. So then what do? You fine tune with that data, but rather than just deleting all the orange data, then you do another step of fine tuning where you remove some of the in-domain data or out-of-domain data, and you keep gradually doing this until at the end, you just kind of fine tune only on your in-domain data. So we were looking at this for a couple of different tasks, but one of them was this ACE data set, which is the automatic content extraction. It's a 2005 data set that comes out of one of the government funded programs. It's in English, Chinese, and Arabic, and there's a lot of semantic parsing tasks in here. Specifically, we focus on some trigger ID and argument ID. But basically in this one, what we did is we treated a foreign language as our in-domain data. And so like English was out of domain, and we treated Arabic as in-domain. And we trained this model where you train it with both English and Arabic, and then gradually over time, just remove the English data until you have a model that's only on Arabic. So this is another one of the strategies that you can approach to actually making your models go beyond English. So in our experiments here, basically this is really interesting. So this is one of the categories we looked at, was this trigger ID. So the bar on the left here, again, this is an F1 square where higher is better. If you don't do any fine tuning and just train on Arabic, you're getting a score of 64.77, which is decent, right? I guess in this task. These numbers don't necessarily mean anything to me. But if you do no fine tuning, so you put in all of the Arabic and English, the model actually does a little bit less, about 0.6 less. So this is just saying like, hey, when I don't do any fine tuning, this English data somehow is confusing my model. So it's better to just train on only Arabic. However, a lot of times people are always talking about fine tuning, right? So in this one, the third bar, what you do is a one-step fine tuning. So basically you take all your Arabic and English, you train a model, and then you just fine tune only on the Arabic data. And this does worse than only using the Arabic data, right? Again, these are sort of these catastrophic forgetting tasks where people are thinking, okay, I can naively just use this data. It's going to work really well, throw it into a model, and no, it doesn't. So you do need to actually think about the problem a little bit and investigate it. But what's kind of nice is when we did this gradual fine tuning, we got pretty large gains. So again, you're starting with Arabic and English and over time gradually removing the English. And this is actually teaching the model how to learn some of the task a little bit better in a low resource setting. And you're going across languages, which is quite nice. Yeah.
Sorry, can you describe the differences between no fine-tuned Arabic and one-step fine-tuned?
Yeah, no fine-tuned Arabic is you're only using Arabic data. The one-step fine-tuning, you start with Arabic and English together, and then you fine-tune with only Arabic. So you're starting with more data, and generally people think more data is better, but you start with this more data, and then you fine-tune on English, and it's actually, or sorry, Arabic, and it's actually hurting. So this works on a lot of other applications we've been looking at. So there was actually some WMT submissions. Yeah.
Sorry, I just want to get a question. What's the difference between gradual fine tuning by manipulating the data versus manipulating the learning rate?
Yeah, that's something I think they're related. I don't think we've done enough investigation into that to answer that fully, but the learning rate over time, you're still seeing English examples. And I think there's a lot of signal in the, like, say the Arabic examples here. So I think that they're probably related and maybe there is a formula between them, but I think honestly at a certain point, the English data, like your out of domain data is probably hurting in this very low resource setting. So again, you're just trying to nudge it in the right direction initially so that it's learning something. And again, I have a feeling that these are sort of local optima. I don't have a proof for this, but I have a feeling these are local optima. And so maybe English is one local optima, Arabic's another one, and they're not finding each other. But if you kind of nudge them together initially and then fine tune more on the Arabic, you're leveraging certain parts of the language. Because you're looking at these large models with tons of parameters. Even if you're freezing your language model, there's a lot of parameters on top for the size of the data that you have.
Yeah. And I would say like if you were over parameterized, would that not be the case? That there are more parameters at the problem. Whereas like this is only the case where you're using all of your parameters already, which is all, and you have to reuse the same parameters for both languages, right?
Yeah, well, I would say that we're probably over parameterized. Well, let me think about that for a second. I would say that there's so many parameters in these models and so little data that probably not, that we're probably not using all of it. And it's an overfitting thing is my guess more than anything, and this kind of prevents it. So maybe there's some sort of data robustness here. There's a lot of open questions. Every time we do this, there's a lot of work to do. And so this is one of the reasons I'm saying we should be working beyond English and NLP is because they're all of these things. So it's been kind of fascinating to see. Another thing in the paper we had was this dialogue state tracking that worked really well. You could do something like train it on hotels domain, and then it would work well on restaurants, even though these were very, very low resource settings. We have some interesting results coming in on code mixing, which I'll talk about in a little bit. But also I started seeing papers like at WMT, like in the shared test at WMT, where they've decided to start gradually fine tuning using data within this. And so in a machine translation setting, like people are using this method and it seems to be working. So that's kind of a nice thing that we've seen as well. So there's a lot of other curriculum learning papers out there. There's a whole set of questions of how do you select the data, right? Like maybe certain ones are not. Is there token overlap? Is there some sort of perplexity measure? There's a lot of questions that are still unanswered about this. But again, this whole talk is my call of like, come on guys, let's use more languages, or come on guys and girls, or come on everyone. So yeah, it's been used in a lot of other things. But yeah, fine tuning is also, you're seeing a lot in tasks, both as papers are being released by large companies, and they'll even do some fine tuning tasks in this. But there's a lot of questions there about other languages as well. And how do we generalize our methods beyond it? So here's another one. It's a machine translation here. So this one is MBART. Has everyone heard of MBART? Okay, there's at least one person in the room, which is good. So yes, MBART is not MBERT. This one is very similar. It's a sequence to sequence model as opposed to an encoder. kind of helpful to think about a lot of these methods now is encoder only, decoder only, or sequence to sequence. I saw a talk by Sasha Rush where he talked about it. I don't think he was the first one to really classify them this way, but this is a really nice way to think about these models now. So an encoder model is like BERT, right? You can think of it as encoder. A decoder model is an autoregressive one like GPT where it's generating a sequence. And a sequence to sequence model is traditionally how we think of like a machine translation model. So you have some sort of sentence being encoded and some sort of sentence or sequence that's being decoded. So MBART is just monolingual. It's not actually doing translation initially. So you'll have various sort of noising functions, and MBART is trying to get out of them. So there's a word masking token operation. There's also a sentence shuffling one. So if you look in the upper left corner here, you'll have something like, this is in English, where did blank from, who blank, I blank, right? And then the correct thing in this thing over here is going to be, who am I, where did I come from, right? So you see the sentences have been swapped, words have been masked out. You put this through the encoder, through MBART. Japanese one here, similar sort of thing, they're applying operations. But all that's happening in these models here is it's learning a monolingual representation of language. Again, these are these language models where this one here is learning a sequence to sequence, but it's learning very good monolingual representations. There's not necessarily any translation here. However, this is actually from the paper, they show that then you can take this nice pre-trained model and you can put in some English and then have it learn to do Japanese by actually fine-tuning them by text. So you're actually showing it English-Japanese pairs, and you do a fine-tuning step on this, right? So this is another way that you can make things more multilingual. So we don't have as much by-text, which is actually human translations out there, as we do monolingual data, right? So how can we leverage monolingual data? Throw a bunch of monolingual data, learn good representations, and then fine-tune with smaller amounts of it. And this seems to work very well on a lot of translation tasks. So, we had a question, this was just presented like 2 weeks ago. What happens when we have some very low resource setting and we want to do some domain adaptation? So we want to do machine translation in a very low resource setting. That's not necessarily, hey, I'm translating Newswire or TED Talks where we have tons of data nowadays. And so we kind of had a question of, okay, so if I have a small amount of this data, and I'll talk through this using COVID as an example, some COVID data set. What if we want to do a standard bilingual machine translation system? Maybe it's better just put in this bilingual, train it like we've always done from scratch. Or do we want to use MBART? So that was kind of the first question. Is it better to use these models, which has seen a lot of data, but hasn't really seen data necessarily in our language or our domain? And then we looked at some examples. Okay, so if we're going to fine tune this, do we want to fine tune initially on the domain? So say the COVID domain, or we did Twitter, we did a few different things. Or language first, is it better to try to take this model, which is already multilingual, and rather than adapting it to COVID, be like a COVID MBART, do we actually want it to be translation first? So pictorially, basically you can read this top to bottom. What you have is this multilingual pre-training in both columns. So this is your standard MBART. And then what we looked at is what happens if you try and learn the language pair. So make it a translation model, say, have it translate Farsi into English. And then we learn the domain of COVID. So now we have a domain adapted translation model versus the other sort of scenario we looked at is we learn the domain. So say we learn this COVID domain, and then we learn the language pair. So now we have an MBART that knows all about COVID, and we're trying to have it learn to now translate COVID Farsi text. So yeah, the data set here, as I was mentioning, is TICO-19. This is a translation initiative for COVID-19. This was pretty quickly crowdsourced to generate it for a bunch of different languages. COVID terms of like flatten the curve, stay at home, certain things that were coming up all the time that 2 years ago that people hadn't heard before. But it's really, really small, right? This is a new language, and there's only, or sorry, this is a new sort of terms in these language. No one had heard the term COVID-19 before. This isn't in our models, right? And we have 971 sentences per language. So very, very, very small. When we're talking about machine translation systems now, like I will say, okay, anything less than 100,000 sentences is probably low resource. Above that's kind of medium resource. I'd say maybe 1 to 4 million sentence pairs is going to be kind of a high resource language, but that's because I'm at a university. If I talk to people at like Microsoft, anything 4 million or below, they're still looking at me like I'm crazy. They're still in a low resource setting. But you can see this is orders of magnitude less than what most people would even define low resource as, right? So this is like 1% what I define low resource as, very, very low resource. And so in our experiments here, you have this TICO, and so the different colors are different languages. Blue scores, again, higher is better, right? If you just do a bilingual baseline, this is, you take it, you download some sort of model where you're going to have your transformer sequence to sequence, you throw in a bunch of Arabic into English, Farsi into English, Portuguese, you get these scores, which are not terrible necessarily. If you have a blue score above 20, people are generally okay with it. If they're above 30, they're going to be pretty happy with the translation. So these aren't terrible. But when we do this MBART baseline, where we kind of have this one step of fine tuning, this really nice model that's been pre-trained on all this data is actually hurting performance, right? If we have another one where we take this model and we train the domain first, right? So we take MBART and we decide we're going to make it into a COVID MBART. It actually doesn't really help either. So, but when we have this other setting here where we take MBART, we actually have it learn to translate the language first and then make it a COVID translation when it works pretty well, which is kind of surprising to us, I would say. But yeah, so you can take these models and you have MBART and you make it a very good translation model. So already you have a much better translation model basically than you would from just scratch. And then you can fine tune on domains. So again, this is multiple steps of fine tuning, not necessarily gradual fine tuning, but there's different ways to, hey, use all of these large resources we have out there to do something else useful with it. So, and what was really amazing to us is Farsi and Portuguese aren't even in MBART pre-training. So, I mean, we're using subword units, but Spanish is probably close to Spanish is close to Portuguese, and I guess maybe the script of Farsi is useful enough, maybe, but we don't have these languages in it. So what's amazing is we're able to generalize to languages that this pre-trained model wasn't even trained on, and they beat rather than training from scratch on these low resource data sets. So this is another way we can really leverage resources we have out there, even for languages we're not expecting to get other stuff. So I'll pause here for questions because this was kind of a surprising thing to us. Yeah, Jeremy?
Yeah, just interesting. Are words for close languages are what's that? Or is it beyond each topic?
Yeah. Yeah, we looked at some lexical overlap. I don't remember what the answers are on this. Neha, do you remember? Yeah.
So this is the in-domain fine-tuning is also multilingual. Right?
Yeah.
From this translated data set.
For the one on the third bar, that's what we did. On the last one, we tried different settings, but no, at this point, it was better just to keep, like if we've already trained it to be a Farsi English translation system, only show it the Farsi in-domain data then.
Okay.
Yeah.
Have you experimented with also adding, so sort of, you have this like fine-tuning pipeline, and have you experimented with adding like in-domain monolingual data for a different language? So like I assume there's a ton of in-domain COVID data for English, much more than Farsi probably. And
right.
So you could like add that in maybe like earlier in the pipeline.
Yeah. So I think we only use the by text in these things, but no, that's a good question. Yeah, I don't know. The way that I saw this, though, it seems to be that this model likes to learn translation first before domain. So, but yeah, this is another one of these kind of exponential problems in terms of experiments that could blow up. But it's a good question. And yeah, if we had some sort of English output of MBART that was better at COVID, but already you'd expect that to be the case with the domain training first, because all of these are the same COVID terms, right? So already it's seen it across 5 languages 5 times. So I don't think it probably would help that much, because that would already be on the decoders. The more I'm talking through it, yeah, I'd say I don't think it would probably help.
Yeah.
If we had only monolingual COVID data, maybe, but yeah. So yeah, so those are just a couple ways that fine tuning can be quite useful for these models. So as I've walked through and just kind of taken a step back here again, we've talked about different ways you can do this. Is you can use 0-shot, you can use some few-shot. All of these, the way when you actually start looking at your data and these problems, you start learning interesting things. You can do silver data, then you can do fine tuning. But what's kind of nice is when you start working on these problems, right now I've kind of shown you some things that are a little bit like algorithmic, but also some kind of engineering insights into how these models will work. But what's kind of fascinating is you can learn a lot more about these models when you actually start doing some of these methods in other languages and really dig into insights. So this was an interesting low resource machine translation thing. So Tuan Nguyen, he's now at Amazon, but he was at Notre Dame, had this idea basically where he was taking IWSLT data, which is TED Talks, so you know the next sentence within a document is probably going to have similar context, similar discourse, right? And so you would have this English to Vietnamese thing, and you say, I think back, and I'm not going to be able to pronounce any Vietnamese, so I'm not going to bother here. And then you'd say, I think back to my father, right? So you can see this is, they have similar context. There's going to be any sort of co-reference resolution. You would assume would actually be useful because they're in sequence. So he had this idea where you concatenate the two sentences together and add this to your training data with the two translations. So you now have more discourse phenomena. It's like, okay, what if we have two sentences, right? Does this work? And across like 4 different languages, you got an average gain of 1 blue point, which normally if you're trying to publish a machine translation paper, that's kind of the threshold that will make reviewers happy and people think might be statistically significant. So that's kind of nice. And so he's like, oh, is this discourse? And there's actually some other papers out there that were claiming this to be discourse. However, I think a lot of times we're willing to trust things in our models that don't actually exist out there, right? So you'll have something about, okay, this is discourse. But then the suggestion was, what if we take 2 random sentence pairs, right, and concatenate them together? So there's no discourse phenomena because it could be from different talks. And that got a 1.1 blue gain, right? So very easily, people will look at these things and say, hey, this is a discourse phenomena, and they haven't actually shown it. So again, this is, as you start generalizing beyond English, you start seeing other things. So no, it's not discourse. So this is where I was talking to him, and then he went and did a bunch of ablation studies, and this was really nice, and it made for a great paper, and I was happy to be involved with it, but I'm going to say this is all him on this part here, really give him the credit for this. So 4 language pairs, and he really did ablation of, okay, how much of this could be positioned? So the hypothesis he had here was, this is the transformer, you have these positional encodings, right? But because it's a low resource setting, you haven't seen a lot of data before. And so you might see the word like Hopkins, right? And it only appears the second position in a sentence. Even though if you had a lot more data out there, maybe it would appear later on. Position, one specific position for a specific token because we just don't have enough training examples. So that was, okay, connection's unstable. Okay, hopefully it's not too bad. So this here, in a low resource settings, you've only seen the words in one position. But can the model learn how to use this positional information was kind of the question he had here. So maybe this is what was happening. And he experimented without concatenation, but shifting the encodings exactly how they would have shifted for when you concatenate them. So basically the data had about 1/3 of concatenated in it. So he shifted them based off of the frequency in the data. So basically it's identical sort of experimental setup, but you don't have concatenated sentences. They're just all monolingual with some padding and shifting so that the model's seeing different things. And this accounted for about 0.2 of the blue difference there, right? So it's not like, oh, there's this smoking gun that solves everything already. Then another kind of question he had was context. So this is in the multi-head attention of the transformer. Each query word can attend to any keyword, right? And so the question was there of like, okay, here in this low resource setting, in a high resource setting, it can learn what not to attend to, right? Because it sees a lot of negative examples. But in a low resource setting, maybe it's not actually learning this. It's only seeing examples once or words occurring once. So maybe it doesn't have a good idea of what context is. So like positive normally would be like, hey, the model's learning that there's the correct contextual information, that somehow this is functioning in a specific way as a verb or something, and that it should be ignoring all these other parts of the sentence that really don't have any part of the translation. And so the way to do this was he took the concatenated methods here and he masked the attention so that they couldn't see across it. So the theory here is maybe it was seeing more negative context because it was seeing negative context from random sentences before across other words. Here, it's only able to see the attention of itself, basically. So in the normal sort of setting, they're still concatenated, but the attention's not going across both sentences now. And this is just to try and measure contextual awareness of these models. And this accounted for about 0.4 of the blue difference, right? So just being able to see different contexts is probably very useful for these models, which is why this sort of data augmentation of concatenating random sentences was working. I'm running a little bit low on time, so I'm going to go pretty quickly through this. The next question you had was length diversity. So most of these models, what you do is when you're creating mini batches to train, you sort them by length. and then you have it so you don't have a lot of padding tokens and it's more efficient for your GPU, right? So what could happen then when you start randomly concatenating, so your mini batches are created by size, is now you could have this more diversity if you've concatenated 2 sentences together, right? And maybe this is now giving you more length diversity, which is very useful for the model to learn different lengths. And this is something that's been seen in some other works, that length actually matters to transformers. So does randomly concatenating cause more diversity? Experiment here is he, after sorting, only randomly concatenated within bins. So this basically would get rid of any sort of chance that you would get more length diversity that way. Like I said, I'm rushing a little bit through this for time, and that accounted for about 0.2 of the blue. And he did a little bit of other stuff, but you could figure out that there was a lot of insights to the model of how the transformer was actually working. So there's some positional encoding, there's a length diversity, and then there's contextual stuff in the attention mechanisms that were all really mattering. And again, this is something that came up because we're trying to work in a low resource setting outside of English. So yeah, so I'll pause for questions on this one at the end and try and get through the rest of the talk. But then last thing is just, okay, besides modeling, can we actually get some insights into language? And this is some ongoing work, which is code mixing right now. So a lot of you have probably heard code mixing. A lot of you are bilingual in here and probably do it without even thinking about it. But this could be code mixing or code switching, is where you kind of switch languages in the middle of a sentence or document. So like nosotros vamos a clase in Hackerman Hall on the Homewood campus, right? Because maybe you're used to saying this place that in English as opposed to in Spanish, right? So code switching is kind of an interesting problem. And we'd like to know if there's some patterns or linguistic insights. And people talk about this a lot of like, okay, in code switching, this is the case. Or you'll see these models where they try and generate synthetic data and they'll do parse trees and reorder parse trees. But one of the main problems with this is, again, it's a very low resource problem, right? There's not a lot of code mixing data out there. And one of the reasons is it occurs a lot more in speech, right? We don't have it necessarily in text. You get a bit of it from like Twitter and some other stuff, but then it's also tough to observe because as soon as I talk to someone who does this, because this is not something that you're trained to do, you do it naively. Once you start trying to observe this data, it changes the patterns, right? So there is some data out there, mostly in like tweets and other social media. But what a lot of people do is some synthetic stuff. So what we've been looking at right now is this nice thing where we've decided to take it and just treat it as kind of gibberish. And again, this goes back to the last thing I was talking about of like, hey, we have these nice transformer models, but maybe they're learning something that is maybe lexical specific to something. And so it's not useful. So what we've done is taken our code mixing data and just replace it with some gibberish tokens, right? So this is kind of like a masking thing, but we've tried with different numbers of gibberish and some other things, but we take the foreign language and we just kind of put it in as a gibberish. So now the model starts to learn like, hey, maybe I only get to pay attention to the part that's in English and that there's some sort of structure. And we'll do some gradual fine tuning where then we add the natural data back into it based off of some other stuff. But what's kind of cool about this is you can create more synthetic data easily. So you don't have to do a lot of these really complicated methods that are out there where people are like, oh, I replaced these noun phrases with this. And it's really not clear that they actually have done any of this. And it can cross language pairs, which means now we can take some of our like Spanglish, oh, it's just Spanish and English code mix data, mask it out, and then add it to our Hinglish when we're trying to do a Hindi English task. And what's kind of cool here is that we're now able to use something, and there's some sort of native stuff that's going on in code mixing that is going across languages. So this is ongoing work right now, but I think it's kind of cool to show that we can get some linguistic insight by trying to think about augmentation and low resource for these things. So yeah, you can use Spanglish data to improve your Hinglish now. And that's probably saying there's either something in the language or maybe something in the model. And that's kind of cool to know that these are things that when we start playing around with other languages that you start to learn. So just briefly, some preliminary ones. This seems to be, the synthetic data works really well as you go into a lower resource study. So this is Malayalam on the right, which only has 1,400 examples of code mixing, right? And this is a 3-week sentiment classification task we're looking at, which is negative, positive, and neutral. But you can see like absolute F1 score improvements. As you go into lower resource settings, you're getting more and more gains. And this is useful because code mixing happens in a lot of languages, but there's very few data sets out there for most languages where this happens. So yeah, this is a way to actually leverage data beyond it. So basically, yeah, so these are some of the lessons learned from generalizing beyond English for stuff. So there's everything from engineering of like, hey, we can do things in 0 shot. And we're able to do this because these models project into a high dimensional space that is maybe somewhat language agnostic. But we're also able to create silver data now, and there's various ways we can actually fine tune models. And I just wanted to kind of actually show the work that was talked about in this talk. So first one is this Colbert X. Here's all the co-authors on this paper, who especially want to highlight Suraj and Eugene, the two left pictures here, who did a lot of the experiments for this. This one is the stochastic gradient surgery, and this one is work that Howard was doing. Oh, it has clicked edit text. I thought that'd go away. Everything is all it takes. I went through this one pretty quickly. This one had so many people I couldn't put all their photos up there. I apologize. This gradual fine tuning. This is the fine tuning MBART paper. This is the low resource machine translation one that I was talking about. And this is ongoing work with Stella, who was doing the code mixing at the end and has some cool, interesting preliminary results. And with that, I'll pause and see if there's any questions. Awesome. It was so clear no one had any questions. Yeah.
I have sort of a broader question, I guess, which is to what extent you think that the kind of current models that assume that you have a lot of training data, at least in some languages, are kind of gambling on the notion that there are enough commonalities sort of universally between all languages that you can have, as Dave said, you have a really good multilingual model. You can add in these new languages like Portuguese and Farsi, and the model will still be able to do something with those languages. Do you think that we're kind of gambling on the idea that they're all languages are similar?
Yeah, I think we're gambling on that right now. I think that we have very much selection bias even with this. So it's not like I'm going out there and getting a lot of languages from Indonesia or something, right? You kind of hope with some of these that maybe there's enough language families represented that maybe this would be the case. A lot of languages are not written, so speech is a whole nother modality that's a big issue on this. But script is another thing. So I've seen some work, and there was a talk that again in the spring where someone was talking about how they took Uyghur data, transliterated it into the Latin script, and were able to leverage some of the Turkish data, right? So that's because they're related languages. So I think if you have related languages, that maybe this is the case. But yes, I think we are just kind of gambling on this. And I also think that there's a lot of these work really well, and we have low hanging fruit right now, right? Like, so we're able to get these huge gains. So why not start here? But this is more just a call of, hey guys, let's do a lot more. Hey everyone. Yeah.
Well, I have a question regarding the silver data.
Yeah.
You have mentioned that people from Microsoft and research companies say that like 14 million resource.
Yeah.
Well, I would assume that there is a huge amount of redundancy in those sentences. So isn't like the resource setting or silver data creation much more about like creating diverse sets of sentences than about creating one?
I think it's both. I think the language is so expressive that 4 million sentences probably has some redundancy in certain bits that's going to follow like the Zipfian distribution. But I also think a lot of times people are cleaning the data, trying to filter out stuff, so there might not be the case. Also, there's going to be the sort of case of like, hey, maybe these things look really redundant, but you're actually seeing some sort of interesting linguistic phenomenon here, right? Like this is when you're translating out of English into a morphologically rich language, maybe it's getting gender for both male and female, right? So I would say that probably 4 million sentences or whatever doesn't actually account for as much of language as we think it does. But overall, the goal is probably in this low resource setting, when you're creating the silver data, is just to create anything you can right now. So yeah.
I have another more specific question. So in the gradient gradient projection paper, there was the heat map, and there were 2 columns in the heat map.
Yeah.
It seemed like they had like no gradient similarity at all.
Yes.
Which,
So that's Japanese. So this one white one here is Japanese with most other languages. So it's probably script for that one.
Yeah,
So over here on this one on the left is English. And I think that's because it's with so many other languages that it's kind of, but then if you kind of look down here, these ones, the clustering here is some other scripts as well, but I guess it's just Japanese.
so it's like mostly just a script.
Script and language family is kind of how we were able to classify more than anything. It's a very it's a qualitative, not quantitative assessment there.
Was this with, or is the data set balanced across languages here?
In this one, because we're doing few shot, yes, there's only 10 examples in each language.
Okay, right, okay. So it's
So-
not just like,
No,
but still the pre-trained model might just have like a really strong gradients.
yeah,
Or like really small gradients for English.
Right.
because It's seen so much English data.
yeah,
And it's seen like maybe more Japanese data.
right, exactly. So,
Like similar languages.
mhm. Cool. Well, thank you.